Hello students. So, in the previous class we started with the vector calculus part of our syllabus, and we introduced the concepts of vector function and limit of a vector function. How do we define the limit using epsilon delta definition, and some results which are basically motivated from the function of scalar function from the function of scalar variables. So, like I was saying in the previous class that like the function of scalar variable, like the scalar functions, sometimes I am confusing these two terms basically during the pronunciation. So, do not get confused. So, during the scalar functions we introduced the concepts of continuity, differentiability. So, in case of vector functions as well we have those concepts valid. So, let me introduce the concept of continuity, and then we will go to the definition of differentiability. So, what do we mean by continuous function? So, continuous vector function. Continuous vector function. All right. So, a vector function f is said to be continuous a vector function f is said to be continuous for a value or at a point, for a value t 0 or at a point t 0 of t if f t 0 is defined and for any given arbitrary small positive number epsilon, there corresponds or there exists a positive number delta such that our f t minus f t 0 is less than epsilon whenever t minus t 0 is less than delta. And if this is true, then the function f is said to be continuous at the point t equals to t 0. Here in case of limit we were only interested what is the value when t is going to t 0. So, we were not interested the value of the vector function at the particular point t equals to t 0. But in case of continuity, like scalar functions, we are interested in the value of the function at the point t is equals to t 0 as well, because if the function f t minus f t 0, if the absolute value is less than epsilon, only then we can say that the function f t is continuous at the point t equals to t 0. So, in this case we actually want to know what is the value of that vector function at the point t equals to t 0. So, it is pretty much motivated from the continuity definition of scalar functions, and it is not that different actually. However, here when we evaluate this mod, we have to consider the individual component and take the absolute value and try to obtain this how to say criteria. All right. And for example, we can have let us say a function, a vector function of type I am writing r or r t equals to f t equals to let us say t cube I plus 4 t square j plus sin t k. Then verify the continuity of f at t equals to, let us say, pi by 2. So, of course, the function is continuous at t equals to pi by 2, because at f pi by 2 at t equals to pi by 2, this is basically f pi by 2, we will get a value, then we will do that epsilon delta definition, and we can be able to show that the value can be made arbitrarily small. And here of course, you can have an interval instead of having this point, because this is an algebraic function, this is an algebraic function, this is a trigonometrical function. So, you can even choose the interval as 0 to pi by 2, and this vector value, this vector function is continuous throughout this interval as well. So, it is a really nice behaving vector function, and therefore, it is continuous even in that interval also. So, now what we will do is we will define the differentiability of a vector function. So, let us define differentiability or derivative. Let us write derivative of a vector function. All right. So, like function of scalar functions, we can also differentiate the vector functions as well, but in which context do we mean? So, for example, a function like y is equals to f x equals to, let us say, x to the power 10 is 10 times differentiable. So, it is a very nicely behaving function, basically a polynomial function, and you can be able to differentiate at least 10 times, because the exponent is 10. However, if we had a function like let us say y is equals to f x equals to 1 by x, and suppose you want to check its differentiability at x equals to 0, then of course, it is not a differentiable function at x equals to 0, and mainly because it is also not continuous at x equals to 0. So, similarly, we can have similar kind of situations in case of vector functions as well. So, how or what way we can define the differentiability of a vector function is the question here. So, in case of scalar functions, you remember we used to take x plus delta x, and the value of f at x plus delta x minus f x is defined as the divided by delta x is defined as the derivative. So, here also we will do the similar thing. So, the definition would be, so suppose if we have a curve like this. So, this is basically our f of t. So, this is the vector function, and that is the origin, and this is my vector r, and this is the point p. Now, this curve can go like this, and then this will be point q. All right. So, point p and q, and at the point p we have the point we have the vector r, and at the point q we have the vector r plus delta r. All right. So, this is how we define this, and let us now put everything in words. So, let r is equals to f t be a vector function of the scalar variable t, and we define r plus delta r. So, the point q basically as f of t plus delta t. So, that means from here, if I write r plus delta r minus r, then this will be basically f of then this will be basically delta r equals to f of t plus delta t minus f of t. So, that is this small how to say movement from p to q. So, this small arc is our delta r, and the delta r is defined in this way. Now, if we consider this vector, so consider the vector delta r by delta t, then this will be f of t plus delta t minus f of t by delta t. And if I make delta t goes to 0. So, if delta t goes to 0, then limit delta t goes to 0, delta r by delta t equals to limit delta t goes to 0, f of t plus delta t minus f of t divided by delta t exist. So, or if delta t goes to 0, so instead of then we can write such that. So, such that this exists, then the value, then the value of the limit, then the value of the limit is called the derivative of the vector function f, and it is denoted by dr dt. So, when t goes to delta t goes to 0, then this right hand side, basically this right hand side is basically if the limit exists, is called as the derivative of the vector function f, and it is denoted by dr dt. All right. So, for example, if we have a function, let us say r equals to t square I plus t to the power 4 j minus sin t k, then its derivative dr dt will be 2 t I plus 4 t to the power 3 j minus sin t is cos t k. So, we basically differentiate every component. So, when it comes to differentiating a vector function, which is given by r is equals to f t equals to f 1 t I plus f 2 t j plus f 3 t k, then in that case the derivative is dr dt given by df dt, and then this one is df 1 by dt times I, df 2 by dt times j plus df 3 by dt times k. So, these are all functions of t. So, this is how we differentiate a vector valued function. So, we differentiate every component, and if any one of the component does not exist at a given point, then in that case the vector function is not differentiable. So, suppose we are evaluating the differentiability at t equals to 0, and we have, instead of t to the power 4, we have 1 by t. Then in that case, of course, the second component is not differentiable, and therefore, the overall vector function would not be differentiable. So, if we want to talk about the differentiability of the vector function, we have to talk about the differentiability of each individual component or each individual scalar function involved in that vector function. So, that is how we define the differentiability of a vector function. All right. Now, like a function of one variable or scalar functions, we had y dy dx, let us say y 1 equals to f dash x, then we had y 2, which is d square y, where dx square equals to f double dash x, then we had y 3, which is basically d 3 y by dx 3 is equals to f triple dash x, and dot dot and so on. So, y n equals to f n x. All right. So, similarly, we have such rule for the vector function as well. So, if we have r equals to, let us say f t, then in that case we will have dr dt equals to f dash t, which is basically df dt. Similarly, d square r by dt square equals to f double dash t Similarly, d3 r by dt is dt3 is equals to f triple dash 3 t and dot dot so on. So, you can do successive derivative for the vector functions as well. So, you can differentiate a vector functions as many times as you want if it is differentiable that many times. All right. So, this is how we define the derivative of a vector function or successive derivative. So, this is basically called successive derivative, and continuity or limit rule, we also have rules for some difference product of vector functions and their derivative. So, theorem 2 you may call. So, let a and at and bt be two differentiable vector functions. And then, so the first rule is d dt of a plus b is equals to dA dt plus dB dt. So, that means differentiation of the sum is equals to sum of the differentiation. All right. So, secondly, if you have subtraction, so differentiation of the difference is equals to difference of the derivative. So, derivative of the difference is equals to difference of the derivative. Third is the dot product. So, derivative of the dot product is equals to a dot dB dt plus dA dt dot b. It is like differentiation of the product of two functions. So, in case of differentiation of product of two function, which was something like d dx of let us say f x times g x. So, it was something like df dx times g plus f times dg dx. So, we used to differentiate one function leaving another and then differentiation of second function leaving the first function. So, it is the same rule here, and since we have a dot product is commutative. So, we can play with this a little bit and we can arrange this dot product. So, because of the commutivity of the dot product, we can write b dot dA dt. So, that is the dot product, and if you have let us say the cross product d dt of a cross b, then it is defined as dA dt cross b plus a cross dB dt. So, this is the cross product rule, and we have to remember that here we cannot change the order, because if we write b cross dA dt, then we have to put a minus sign. So, a cross b is equals to minus of b cross a. So, that's what we have to take care of here. Now, similarly, if we have let us say a scalar function which is multiplied by a vector function. So, I have phi t, which is also a differentiable scalar function, and then I have a vector function say a t. So, then in that case it can be written as d phi dt times a t plus phi t times dA dt. All right. So, it is just that there would not be any kind of dot or cross here, but it is just that the function phi is multiplied in usual multiplication sense. So, when I say usual multiplication sense, it means that if we have a phi times a t, so let us say our function a t is t square I plus t to the power 4 j, and my phi function is something say a constant, basically say 2, then in that case it will be a usual multiplication of these two scalar quantities. So, it is 2 t square I plus 2 t to the power 4 j. So, it will not be like a dot product. So, a dot product will usually give you a real number actually, but in this case you will still get a vector function. All right. Now, if you have, let us say, instead of a scalar function and a vector function, we can also have dA dt times say vector A, vector B, and sorry, A cross. Let me write this formula properly. So, we can also have something like A cross B cross C. I cannot have A dot B dot C, because then B dot C is a scalar function, and that's then it is the same definition here. All right. So, we are not writing that formula. So, here in this case it will be dA dt cross product with B cross C plus A cross dB dt cross C, and then A cross B cross dC dt. All right. So, again we have to take care of the order. So, here B cross C, and then I have to make sure that this the cross product is here, and then we have a cross product here. So, this is how we will do the cross product for a derivative of the cross product of three vector functions. So, obviously, we treat these two as one vector, and obviously, we treat these two as one vector and this one as another vector, and based on that we can do this derivative. So, basically, we differentiated dA dt times B cross C, and then I used instead of B in this formula, I am using B cross C. So, then our A cross product with this ddt of this B cross C will get common, and then we do the derivative on B cross C, and that will give us the whole cross derivative of the cross product of A cross B cross C. So, there are several other formulas of derivative of vector functions. We can look into any textbook, and there you can find all sorts of formulas, and for the interested readers, you can consult any one of those vector calculus book for more formulas. I have just listed few because we might be using them at some point in the future, and therefore, it is a good collection to have. Now, that we defined these formulas, we can also try to prove them, but it is just that the proof is very straightforward, and it is also present in those textbooks. So, we will not do that for the time being. Next, we will try to prove some basic result. So, let us say remark 1, or so we know that derivative of a constant function is 0. So, that is a very well known result in our function of one variable. Now, what is the derivative of a constant vector? So, like constant function, we also have scalar functions, we also have constant vector functions. So, suppose we have r equals to f t equals to a constant function. So, whose component are c 1 I plus c 2 j plus c 3 k. So, what is dr dt? So, c 1, c 2, c 3 are all real numbers. So, they are all real numbers, and then we have to calculate the derivative of this vector function. So, solution, we have r equals to f t equals to some c. So, from here r plus delta r would be f dash t plus delta t equals to again c, and therefore, from here we will have delta r equals to 0. So, f of t plus delta t minus f of t is equals to 0. So, from here we will get dr del r delta t equals to 0 by delta t, and now I will take limit on both sides. So, this will be limit delta t goes to 0, and then this will be limit delta t goes to 0 0. So, limit of a constant function is basically constant, that particular constant. So, here it is 0, and therefore, dr dt is equals to 0 which is a 0 vector. I can put a vector sign here. So, which is basically a 0 vector. So, like derivative of a scalar function yields derivative of a constant in function of in scalar functions gives us constant. In here in case of vector functions, the derivative of a constant vector will give us a 0 vector. So, this result also holds true from what we have learnt in our scalar functions. Now, the next thing is the next property is we can have it again as a remark. The necessary, we can say that the necessary, another remark, say 2, the necessary and sufficient condition of a function to be constant is that dA dt equals to 0. So, the necessary condition we have proved. So, the necessary condition we have already proved that if we have a is equals to a constant function, then from here dA dt is 0. This is we have already seen, this we have already seen just like a couple of minutes ago. So, this is true. Now, the condition is sufficient. So, that means the sufficient condition is to prove the sufficient condition, we will have dA dt equals to 0. Now, the vector function A has 3 components. So, let us write dA1 t I plus dA2 dt times j plus dA3 time divided by dt times k is equals to 0. Now, this is 0 vector actually. So, this is basically our 0 vector. So, this 0 vector can be written as 0 I plus 0 j, where each component is 0. So, we can write each component as 0, and now we equate the coefficients of I, j and k. So, if we equate the coefficients of I, j and k, then this will give dA1 dt equals to 0, dA2 dt equals to 0 and dA3 dt equals to 0. So, from here if we integrate both sides, then we will get A1 equals to constant, say C1, A1 t equals to constant, say C1, A2 t equals to constant, say C2, and A3 t equals to constant, say C3. So, that means A1 2, A2 2, A1 2, A1 t, A2 t and A3 t are basically constant. So, from here our vector R, from here our vector AT is A1 t times I, A2 t times j and A3 t times k, which is basically C1 I, C2 j and C3 k. Since C1, C2, C3 are all constant, this is basically a constant vector. So, the condition is sufficient as well. So, you see like a function scalar functions, if the function is given to be constant, then its derivative is 0. In case of vector function as well, if you have a constant vector, then its derivative would also be 0, and it is necessary and sufficient condition. So, that means if the derivative is 0, then the function vector function has to be a constant function, and if the vector function is a constant function, then its derivative has to be 0. So, we learnt this basic result in vector calculus, and in our next class we will try to work out some examples on derivative of a vector function, and then we move to our next topic. So, I will stop here for today, and I thank you for your attention, and I look forward to your next class.